So hi everyone, and thanks for coming back. This session we're going to talk about basically massive compact objects, mostly neutron stars and black holes, and also gravitational wave sources, which actually not necessarily relevant only for neutron star or black holes. But I want to make a short intro and try to be really short about it. And it's going to have two parts, one which is really important, and the other which is about the science. So let's start with the important thing. So obviously, the most important question we try to answer is what is the full answer to when and where does common envelope evolution happen and how does it evolve? But actually, most of the people in this audience already answered this. It's a very simple and easy question, as we all know, obviously. And so I decided to actually focus on a different question, much deeper question. And what is this deeper question? This deeper question is, what is the answer to the ultimate question of life, the universe, and everything? And yes, it's certainly not 42, but only a single person in this audience had actually solved this. And it's time we celebrate his birthday. So I don't know if you know what is the answer to this question, but he knows. And the answer to the ultimate question of life, the universe, and everything is, of course, jets. And the person, of course, who knows these answers and tell you whenever you ask him about what is the answer is jets, is Noam Soker. So I'd like to first say that happy birthday to Noam. And he didn't let me actually make a conference for him a few years back. So at least I thought me and also other at least thought that we'll tell him happy birthday to celebrate his birthday, which happens, I think, today. So I would like to ask you for one horrific thing from all of you is to open your mics, all of you, just for 20 seconds. And I'll say 1, 2, 3, and you'll say, happy birthday, Noam. So when everyone ready, first of all, please just open your mics. I know it's going to sound horrific, but still, please do so. Okay, so on my count, and then, of course, turn off your mics. So on my count, 1, 2, 3. Happy birthday,
Noam. Birthday, no, Soker.
Okay,
Haggai, thanks. You wanted to do it at 60, but today I am 63 and I prefer the prime number birthday. So I did it now, 63.
It's a good, very good number. So now I'll follow up with the less important question, which is actually about the science. So I'll try to be brief in order to allow for more discussion later on. So as I said, we're going to talk about black holes, neutron stars, gravitational wave sources, and obviously only some aspects of it, but hopefully we have some time for discussion, discuss more of those issues beside what is going to be presented and that all of these touch upon these subjects. So we know that we have this gravitational wave evolution over the last few years where we actually see the sky in gravitational waves and we can actually see gravitational wave sources. And I think that evolution is obviously important for huge number of fields in astronomy, but certainly also for common envelope evolution, given the constraint it can potentially give us. So I try to gather just a few general questions or issues that relate to this, and I think these are some of the aspects we can discuss later on, but feel free, of course, to raise many other questions. These are just things that I had at the top of my mind. So obviously, common envelope evolution plays a key role in the evolution of formation of compact object binaries, and we know that all the predictions that discuss the formation of compact object binaries involve common envelope evolution studies, because all population synthesis studies use common envelope in doing the binary evolution, but even the dynamical channels that involve global clusters and other kind of dense environments obviously base their works on what kind of binaries do you have at any given point. So even those actually hold inside them population synthesis, which in turn relies on what we think or understand or misunderstand about common envelope evolution. So in principle, the demographics, just the rates and the delay time distribution of gravitational wave sources can potentially tell us and constrain models for common envelope evolution. And we just saw actually in the previous session, Avishai talked about it and the other works about these issues, you can actually get some potential constraints. Of course, it's very difficult to put direct constraints from these observations and rates that we find up onto common envelope evolution, but these do add additional constraint that we have from other type of observations we saw, like those that described by Sylvia. So this is, of course, one of the main issues, is just that really the overall demographics. The other thing is that actually properties, both of the compact objects are involved, like their masses and the spins, but also, of course, the binaries themselves. The spin orbit inclination, spin inclination, all of these are actually really depend strongly on the accretion and the alignment before and during the common envelope evolution. And unfortunately, simulations exploring these issues are still scarce. There have been done some efforts. I think some of these were mentioned already in this conference, but these are really difficult, mostly because we need to really resolve accretion aspects, right? In order to measure the changes in mass, the changes in spins. We can look, try to understand a bit of the alignment during the common envelope evolution, but even those, of course, are related to all the other misunderstood aspects that we have about common envelope evolution, like even the mass ejection itself, whether recombination important, how important it is, other aspects, jets, etc., etc. But these properties do, in principle, rely on this evolution, and therefore are strongly dependent on them. And we need to understand common evolution in order to study them, and vice versa, using those observed properties, try to understand common evolution. Other aspect you can discuss is actually the effects on gravitational wave spirals themselves. What do I mean by that? Potentially, in some cases, and I think Barry will discuss it a bit later, from our work, in some cases, you could actually have the common envelope evolution, the in-spiral itself, already be affecting the gravitational wave source that we see, the actual observed gravitational wave sources. This is more likely to happen in case of white dwarf and cores, and less likely maybe in some case of the Neutron star, but really depends on when and where we see them. So it is actually interesting whether we can really directly even study common envelope evolution during the evolution using observation of gravitational wave sources that show this in-spiral and how it's affected. Other aspects relate to the gas that is left over after the common envelope evolution. This gas could be very important for electromagnetic counterparts, both for Neutron star mergers, and that could be related to even to short GRBs and gravitational wave sources for Neutron star mergers, but also with the potential, some people suggest that you might even have seen or will see electromagnetic counterparts of black hole mergers if you do have some gas around. And if you do have some gas around, this gas should be some remnant probably of common envelope evolution. So these aspects are also very important for these issues of both gravitational waves and their counterparts. I already mentioned it, but I won't talk too much about it because we are right now we're in the LIGO era. But if you think about like 10 to 15 years from now to probably 15 or more years from now to the LISA era, we can actually observe wide dwarf core mergers. Then gravitational wave sources would actually also look on the lower mass aspects of common envelope evolution, and we should keep it in mind and already actually study this issue in preparation for the next era of gravitational wave sources. Another, I don't know if it's side, but another aspect is related to formation of X-ray binaries, which also involve neutron stars and black holes, but in this case, not another compact object, but some kind of a donor. And some of the understanding of these X-ray binaries we see are not very well understood, like low mass X-ray, black hole X-ray binaries, and whether that is involves or related to common envelope evolution or to other type of mass transfer aspect is also an important question. So I've already talked too much, and I just wanted to kind of mention some of these aspects of the issues, and I would like to actually now go to our speakers. So I guess we'll start with Olgado, I think. Right, I'll stop the sharing, and you can actually try and put your presentation.
Ready?
Excellent.
Okay.
Great. So I'll give you a 2 minutes warning. Okay.
All right. Thank you very much.
Thank you.
And then thank you to the organizers for giving me the opportunity to present this work. This was work published earlier this year in collaboration with Hector Silva, Ulriker, and Nico Younes. And I think one of the certainly important themes of this meeting, and I've certainly learned a lot from different members of the community, is breaking up this macrophysical process into smaller chunks and making progress on each chunk so that overall the global picture is improved. So for this talk, I'll focus on, in particular, neutron stars. So double neutron star systems that form via common envelope evolution, and how strong gravity, i.e. general relativity, and the nuclear equation of state may play a role in how it accretes and gains mass during this phase of evolution. And so we've heard various models that have been presented in the literature as well for modeling common envelope evolution. So going from left to right in this summary diagram, though not necessarily mostly comprehensive, going from the analytic model, so the alpha prescription, all the way to full global radiation hydro simulations in full 3D. So for this work in particular, since we're investigating systematically the effect of the neutron star equation of state, I'll be mostly focusing on this semi-analytic model here, where the envelope is assumed to be static, though local drag forces here are computed and informed by Morgan McLeod's wind tunnel simulations, where the upstream density gradient is varied as a parameter, and there his models estimate what the resulting accretion rates and dynamical friction is within this local box. Then, of course, there are certainly improvements that have been made, especially the radiation hydro in 1D as an improvement to the static envelope assumption. And then, of course, there's been recent presentations this week on further improvements in the global models of radiation hydro, and it's been very heartening to see these improvements as well. And so for neutron stars, what happens as they undergo common envelope evolution? So previously was thought, I think in the early 90s, early 2000s, or 90s and early 2000s, that hypercritical accretion would cause the neutron star to collapse to a black hole. Though recently, thanks to Morgan McLeod's work, where they're running these wind tunnel simulations, they find that the upstream density gradient breaks the symmetry of Bondi-Hoyle-Littleton accretion, such that the accretion rate is suppressed, and thus the neutron star, their estimates are that they only accrete about 1% of their total mass from this phase. So in this work, building on top of that, we investigate how the neutron star properties itself, so the equation of state, how that affects how much gravitational mass the neutron star gains. And one of the main features here is that since neutron stars are compact, they are in the strong gravity regime, and thus they have substantial binding energy. And so just as a review of neutron star interiors, so the dense matter equation of state determines the macroscopic properties of neutron stars, so how the radius depends on the gravitational mass, the moment of inertia, et cetera. So going from the outer regions of the neutron star towards the core is where you're going from atomic nuclei down to even more neutron-rich material. And then in the nuclear physics community, it's certainly an open question as to what is the physics at densities greater than nuclear saturation, and whether or not there doesn't exist a hadron quark phase transition into a quark core. So on the right is a summary of different mass radius curves for different equations of state. So how you should think of it is that each point on a given curve is the TOV solution for a neutron star with this given equation of state. So there are some grade curves around here that are not thought to be astrophysically relevant. So the grade curves coming in from the left are these pure Kork-Wanner stars, and then there's some grayed out curves here that are not able to produce a neutron star greater than 2 solar masses, which is not consistent with observations. And so for this talk here, since neutron stars have substantial binding energy, it's about 10% of the total mass energy budget. And certainly another point I'll emphasize is that for more massive neutron stars, they'll have even greater binding energy. So the analogy to draw is that with atomic nuclei, when you add up the total mass energy of the atomic nucleus plus its binding energy, that's equivalent to the total mass energy of the individual nucleons separated. So it's a similar analogy to the neutron star cases when you add up the gravitational mass plus its binding energy. That gives you the total baryonic mass of the neutron star. And so here we're working with a set of equations of state that are consistent with both gravitational wave observations, so GW 170817, and recent X-ray timing observations of pulsars from the NICER collaboration. So with these equations of state, we're going to model neutron star in spiral with simple drag force prescriptions coming from the wind tunnel model, and we'll investigate how this variation in the equation of state affects how the neutron star evolves. So, right, there's certainly been, so these blue and green contours correspond to the constraints from tidal deformability measurements, and the red constraints coming from X-ray timing observations of J0030. And then more recently this year, there's been the release of new mass radius constraints from the massive pulsar J0740, and that has served to additionally constrain our current knowledge of the equation of state of dense matter. On the right is plotting what the gravitochemical potential is for these different equations of state as a function of gravitational mass. So you can think of it as a proxy for how much or how efficiently baryonic mass gets converted into binding energy. And the color here corresponds to this binding energy relative to gravitational mass. So if you don't account for binding energy at all, this gravitochemical potential is equivalent to 1. And then for these different equations of state, they span from around 0.9 to 0.6. And for more massive neutron stars, this gravitochemical potential decreases. And so for modeling the neutron star in spiral, how much matter gets captured into the accretion radius, and then how much the neutron star gains mass and spins up. That's gonna, well, the approach we take is modeling each different relevant length scale with a different semi-analytic model. So, and then this is on the top here, just illustrating the scale separation for this problem. And certainly on the larger scales is where we've seen global models this week and recent developments there. And then for this work here, we're coming in from the micro scale, and hopefully somewhere in between, well, going from these two different directions is going to be helpful in getting a better handle on common envelope evolution for neutron stars. So for the stellar properties, we generate a set of MESA models. And then for the neutron star properties, we're solving the Hartle-Thorne equations. So the general relativistic equations for slowly rotating neutron stars for each of the equations of state that I showed in the previous slide. And so for each time step, we're able to interpolate what the neutron star properties are when it goes from, or when it gains mass and spins up at each time step. And so on the bottom here is the summary of the orbit integration and the neutron star evolution. So where the in spiral is driven by local drag forces, and these are informed by Morgan-McLeod's wind tunnel simulations, which are a function of the upstream Mach number, the mass ratio between the accretor and the enclosed mass of the orbit, and also depending on the sync radius that's used in Morgan's wind tunnel simulations. And so the GR aspect is given here, where the gravitational mass of the neutron star depends on the baryonic mass times this gravitochemical potential that I previously shown, but also this contribution from the spin up, since in general relativity, rotation contributes to mass energy. So I won't be able to describe all the different models we tested, but I'll just show one of the fiducial ones, which is a 12 solar mass star with a 1.4 neutron star companion and with an initial spin of 50 hertz. So
sorry, 2 minutes.
Oh, 2 minutes, great. So the black curves here are for if you don't account for binding energy at all, and these orange curves are where you do. So this is the gravitational mass gain versus orbital separation. And on the right here is showing a closer view on the final spin up versus the final mass gain. So these diamond points are if you don't account for binding energy, and these circle points are when you do account for it self-consistently. So these circle points are much less compared to these diamond points, and the different colors also correspond to different initial neutron star spins. So it's there is an effect, but it's not as much compared to the binding energy effect itself. And also, since more massive neutron stars convert more of their accreted baryonic mass into binding energy, on the right here is plotting the ratio of the gravitational mass gain relative to how much baryonic mass is accreted. And each of these distributions here are for increasing neutron star gravitational masses. And these are all systematically less than 1. And also these different color distributions correspond to different neutron star spins itself. So the more massive the neutron star is, the more efficiently it can convert its accreted baryonic mass into binding energy. And then certainly an important point of this conference that has been brought up is whether or not feedback may manifest in the form of outflows or jets. And certainly for the case of compact objects like black holes and neutron stars, I think an important aspect is looking at general relativistic red hydra simulations of accretion itself onto the compact objects and whether or not outflows form on these scales. Certainly for the difference between the neutron star and black hole case is the neutron star has a hard surface, and that's going to cause material to pile up and might even ignite nuclear reactions that generate energy. So that's something that we're currently looking at as well, and certainly stay tuned for results that come from these simulations. So in summary, due to gravitational binding energy, neutron stars will gain less gravitational mass than what they accrete. I haven't shown any results regarding using equations of state that involve hadron quark phase transitions, but that's certainly something that we're looking into in the future. So one may take away point here is that for more compact stars, they have larger binding energy. And so strong gravity and nuclear microphysics may thus affect both the population properties of neutron star binaries and the double neutron star merger rate. And certainly these results can help inform binary population synthesis models, as well as subgrid models for global common envelope simulations. And with that, I'll go ahead and end here and take any questions. Thank you.
Thank you very much, Miguel. So please feel free, we have a few minutes for questions. Yes, Fabian.
Yes, thank you very much. This was really nice and beautifully worked out. I was wondering a bit about the sort of exact flow of matter close to the neutron star surface and then sort of the accretion and stuff. Because I mean, neutron stars are of course highly magnetic, so they have a relatively strong B field, they have winds. And is it possible within the common envelope or within the envelope of another star that you form, for example, something like a bow shock, and then you actually just sort of distort or you just sort of deflect matter, and then it's just sort of flowing next to the neutron star without being much accreted? And also, how would you expect that, for example, to affect the specific angular momentum that you then accrete from such a flow?
Right. Certainly, we've thought a bit about magnetized neutron stars. So I think, or at least from what we're thinking so far, the flow is expected to be radiation dominated. So I think the radiation pressure is going to be dynamically more important compared to the magnetic field of a neutron star. So that could certainly be very different if it's magnetar level strengths. And then it's an open question as to how strong the magnetic fields may be for if the magnetic fields can be magnetar level when a neutron star initiates a common envelope. So if there is also magnetic fields within the plasma itself, that could induce turbulence in the plasma flow, and then radiation is going to stream faster through the lower density regions. So certainly there's going to be, right, there's the effect of maybe a strong magnetic field for the neutron star and then magnetic fields within the plasma that changes the transport. So that's certainly something that we're carefully thinking about in the future, for sure.
Thanks. Luke?
Yeah, I'm just wondering, I mean, I am familiar with the work by Morgan on that, the accretion rate and so on, but like we also have a paper from 2018 where we look at the accretion rate, assuming with a subgrid model in a global simulation. And we find that the accretion rates can be extremely high. Now, it's not a neutron star, but it's perhaps best it best corresponds to a neutron star case because we don't include radiative feedback. That's an assumption of the subgrid model, and maybe in neutron stars that's somewhat realistic since you have neutrino cooling. So, and we get very high accretion rates. So I'm just wondering, do people think this to me it's not settled? And also I'm aware of there are some, I'm not very familiar, but there are some new papers that incorporate GR into these wind tunnel simulations. And I think they get pretty low accretion rates too from just looking at it right now, but like Cruz, Azorio, and people like that, I'm not very familiar. So maybe you could just comment on all that.
Yeah, I think regarding the recent GR work by Cruz, Azorio, and Rizzola, one of the limitations, if I recall correctly, is that the sound speed of the plasma is taken to be artificially, well, about 0.1 C in order to make the dynamical range more convenient for computational simulation. And I think another limitation or limitation of that study was I think they had that in 2D in the wind tunnel context. But certainly, right, I think these GR simulations are going to be important for getting a better handle on under what conditions a outflow would be launched. But one other uncertainty is, right, this separation in length scale with the accretion radius and the scale of the compact object. It's going to be uncertain as to what are the initial conditions for the GR simulations that they should use, but maybe something where a wind tunnel simulations can give a sense of what is the angular momentum that's accreted into the sink radius. That could at least be a start for getting a better handle of this on this scale separation.
Yeah, and what about the global simulations? Because I mean, there's a question that are the wind tunnel simulations capturing all the necessary physics for the accretion, or do we need global simulations?
Right, the global simulations are certainly going to be important because the wind tunnel approach, because the envelope globally relaxes on the scale of during the orbital end spiral. So there's going to need to be models across all these different length scales, and integrating them all in a physical fashion is going to be where I think we need to head.
Okay, thank you very much. And unfortunately, we need to go back to the next talk, but we can continue, of course, discussion on Slack. So please, I think the next speaker is Javier. Can you put your presentation?
Sure.
Great, thank you very much. And I'll give you 2 minutes warning.
Yeah, sure, thanks. Okay, is it working, hopefully? Can you see my screen?
We can see, but we can hardly hear you. Can you speak louder or?
Okay, hello. Okay, maybe let me try.
Not much better.
I was trying something with optimize for video clip or something like that because I have videos in the presentation, but I don't know if I trust it. Let's try again like this. Again?
Yeah, we can see you. The problem is mostly about hearing you.
Okay. Well, I can speak louder. But...
Okay, so maybe try to just talk closer to the microphone or something. I don't know.
Okay, good.
Okay, good.
So well,
I'll give you a 2 minutes.
Yeah, sure. Hello, everyone. My name is Javier Moran-Fraile. I'm a PhD student at Fritz Röpke's group. And today I will briefly talk about the gravitational wave interaction, the gravitational wave emission generated by some stellar interactions. In the coming years, with the launch of LISA getting closer and closer, some stellar interactions, such as the dynamical phases of common envelope events and stellar mergers, may become even more interesting as they're promising sources for gravitational waves. Recent works, such as Renzo et al. 2021 and Ginat et al. 2020, are a proof of this. They have analyzed common envelopes with semi-analytical models, and their results suggest that these events may be detectable. So we aim to use the full-scale 3D hydrodynamical simulations that we have in our group to see what can we learn from them as a complementary approach. The events that I will show today are basically a merger between two main sequence stars, a failed common envelope ejection, and a successful common envelope ejection. We don't really have the time to discuss any math behind gravitational waves right now, but I think there are a few concepts that we should know today. One is the strength of the gravitational waves, what we call this strain, this H, which is more or less a measurement of how much space-time is stretched with the wave. And it decreases as 1 over the distance to the source. And another key thing is that LISA has different sensitivities for different gravitational wave frequencies. So what we do is to take the Fourier transform of the gravitational wave signal over time and analyze what we call the characteristic strain at different frequencies. Another last key thing about the gravitational waves, the ones released by orbiting systems, these frequencies will correspond to 2 times the orbital frequency of the system. So with LISA's peak sensitivity being around 4 millihertz, the best candidate sources will have an orbital frequency of around 2 millihertz, which corresponds with a period of 500 seconds. So this is a pretty short period, especially if we're talking about main sequence mergers and common envelopes. But the gravitational wave also, the strength also depends on the total mass. So a very massive merger or common envelope could potentially have a chance of being detected, even at a frequency where LISA is not that sensitive. So we carry out all our simulations in the code AREPO, which many people may be familiar with. AREPO is a code that uses an unstructured moving Voronoi mesh. We only use Newtonian gravity, and therefore we have no GR included at all in these simulations. We only compute the gravitational waves as a post-processing kind of thing, so not as an energy losing source. This is okay to do because in the case of common envelope events and the stellar mergers that we are simulating, the energy released by gravitational waves is not the driving mechanism behind these events. They are mainly driven by drag forces and mass transfers. The release of this gravitational radiation is just caused by the rapid changes in mass distribution, but the effect that it has on the orbit shrinking is negligible compared to the other forces involved. So let's move on to the first simulation, which is the main sequence merger. The one that I use for this is the one described in Schneider et al. 2019. It consists of 2 main sequence stars of 8 and 9 solar masses. In this merger, the merger takes place as the primary star starts transferring mass to the secondary, which drains angular momentum and accelerates the merger, and the initially more massive star gets disrupted, and its core merges with the one of the secondary star. So let's see how the simulation looks like and their gravitational waves. So on the left here, we'll have the hydro simulation color-coded with the density, seen from the top of the orbital plane. And on the bottom right, we'll have the strain of the cross-polarization of the gravitational waves. So you can see that the stars orbit each other for a few days as the orbit shrinks due to the mass transfer. The maximum amplitude of the strain grows, reaching the maximum at the moment of disruption. And then the signal basically stops after the merger takes place. So if we analyze the frequencies of these gravitational waves, calculating the characteristic strain, we see that it peaks at around 4 times 10 to the minus 5 hertz, which roughly corresponds with 2 times the orbital frequency at the moment that star is disrupted, which is here in the dashed line. If you remember, LISA's peak sensitivity was in the order of millihertz, so we are a little bit far from it. Indeed, if we compare it with LISA's sensitivity, we see that we are quite off. The signal of the merger here is assuming a distance to the source of 1 kiloparsec, so it's not even a distant source. As you can see, the signal is loud enough, but its frequency is not optimal for LISA. Indeed, the metric that we usually use to estimate the detectability of an event such as this is the signal-to-noise ratio, which can be seen as the overlap between these 2 curves. In this case, as you can see, there's no overlap, so we have a signal-to-noise ratio in the order of 10 to the minus 2. We could build up more signal by observing during a longer period of time, because as you saw, the simulation lasts only a few days, and theoretically, we could just observe this system for a couple of years before the merger takes place, and we would build up more signal. This would increase the strength of the signal at frequencies that correspond with the orbital frequency, but as you can see, LISA is not really that sensitive at these frequencies, so we would still probably be far away from detectability. More massive stars could also release a stronger signal, but again, we are limited by the smallest orbit that they can get to before disruption. So it seems quite unlikely that main sequence star mergers will be detectable unless they're really, really nearby. So in order to get gravitational wave signals are at the optimal frequencies for LISA, we need more compact stars. Otherwise, the disruption will take place before the stars can get close enough. In the case of common envelopes, the initial orbits are definitely too wide for the systems to be detected by LISA, having orbital periods of many days. But as the companion star shrinks down in the envelope, the signal will move to higher and higher frequencies, making it easier for us to detect them. What we call a failed common envelope ejection happens when the companion fails to eject the envelope, and it will keep spiraling inside of it until either the companion or the primary star's core is disrupted. These are really promising scenarios because we will move from low frequencies to pretty high ones before disruption. So if the companion and the core are compact enough, they will get to really close to each other before disruption, and the frequency of the gravitational waves released could reach the peak sensitivity of LISA and beyond. So let's take a look at what simulations we have for this scenario. It is computationally unachievable for us to simulate the whole common envelope phase with a fully resolved hydrodynamical core and companion. So as a first order approximation, to mimic more or less the conditions at the final moments of a failed common envelope ejection, we simulate the merger between two white dwarfs. The conditions in such a merger are similar to the ones found in the last stage of a failed common envelope ejection, where we would have the strongest higher frequency signals. For this simulation, we use a core of 0.4 solar masses and a companion of 0.6. The hydrodynamical evolution of this merger is quite similar to the main sequence merger. In this case, the heavier companion disrupts the giant star's core, accretes part of his mass, and forms a kind of accretion disk. This all happens in a way shorter timescale compared to the main sequence merger. I'm here only showing the final frame of the movie to save time, as it's very similar. The companion orbits the core, basically still in mass per until finally disrupting it. And again, the gravitational wave emission is quickly reduced at the moment the disruption takes place, although this time is not as abrupt because the remnant is not as spherically symmetric as in the case of the main sequence merger. So we have a little bit of noise at the beginning. I think it is important to notice that the timescales involved now are so small that the whole simulation only lasts about 1,000 seconds compared to the potential years of observation time that LISA will have. Despite that, if we look at the characteristic strain, we see that the peak frequency of the gravitational waves is in a band where LISA is very sensitive. This makes it so, assuming same distance as with the main sequence merger, even with our just few hundred seconds of signal, the signal to noise ratio is way larger, of already 3. And observing the system for a long time before the actual disruption will help building up even more signal that will increase our chances of a detection. But again, I have to stress that this is a really first order approximation, as we're basically just simulating the merger between two white dwarfs that are at the point of mass transfer. So we are missing all the signal coming from earlier stages. And as you can see in the plot, if we move from a low frequency up to this point, this will necessarily include a point where LISA is even more sensitive. Another caveat of this simulation is that in a more realistic scenario, maybe we may have a more dense environment that could generate stronger drag forces, leading to an even faster merger. That would also change the characteristic strain. But overall, these failed common envelope ejections look quite promising. And finally, let's move on to a successful common envelope ejection. As I mentioned, the initial separation between the core of a giant star and its companion is too large, and the associated gravitational waves will have too low frequency for LISA to pick them up. The key point will be whether or not the companion manages to spiral down to an orbit with an orbital frequency high enough to be detected by LISA. The simulation that I will show now, the setup is basically the same methods as Christian Sand's 2020 paper, but with a red giant star. And it consists of a 2 solar mass red giant with a compact companion of a single solar mass. As here we were simulating the ejection of the envelope, we used point masses for the core and the companion.
Sorry, this is 2 minutes.
Okay, perfect. In this simulation, the companion's orbit will shrink inside the envelope, as in general common envelope event, and it will keep unbounding mass until most of the envelope is ejected, and at this point it reaches a stable orbit of around 4 solar radii. Okay, so in this case, we can see how quickly the frequency of the gravitational wave of the frequency of the gravitational waves increases as the companion plunges in. Sorry for the quality of the Hydro movie. It's not, my internet is like the frame rate is really low compared to the gravitational wave signal. But yeah, it will take still a few more days to reach a stable orbit, but the gravitational wave frequency has increased so much that we cannot really see anything here. So let's move to the final stages. So here we are at 670 days, where we have reached a mostly stable orbit of 4 solar radii. The frequency is practically constant. And in the simulation, in contrast with previous ones, we don't have a shutdown of the signal. The gravitational waves go from low frequency to a high one, but the resulting system keeps emitting them. Unfortunately, this final frequency reach is still too low for LISA, too far away from its sensitivity range. We would need the orbit to shrink quite below a solar radii for the resulting system to be in a frequency range that could make it detectable. We have analyzed most of the common envelope simulations performed by our group, and in none of them, the companion is spirals deep enough into the envelope, so we have found no detectable signal coming from a successful common envelope ejection. It is possible, though, that we may have some bias in the configurations that we have tested. There could be different setups that could reach tighter orbits, but we have not observed that in any of the simulations in our group. And finally, one of the things that we could test with the simulation is how much information we are losing by treating the source as 2-point masses and ignoring the contribution of the envelope in the gravitational waves. This is a common assumption used in other more simple models. So here I have plotted the characteristic strain of the whole simulation in pink, and in yellow, the strain coming only from the course. And as you can see, the only difference noticeable is in the lowest frequencies, where you have a slightly weaker signal if we only take the course into account. And bear in mind, this is a log-log plot, so this is a really small difference. So we can safely say that the contribution of the envelope to the total signal is almost negligible, and this approximation that is commonly used should generally be valid. And I don't think I have time for more, so I will leave you with a quick summary of what we have done and the caveats to our conclusions. And I'll be happy to take any questions.
Thank you very much, Javier. Very nice talk. So, please, questions. Yes, Amit.
My question is about the main sequence merger. What is the 3D structure of the product, more or less at the end of the simulation?
I think I have listed something. Yeah, you have basically a 14 solar mass core with a toroidal kind of disc shape around of it.
Sorry, I missed it. Okay.
No, I had it on the slide, but I didn't have time to mention it. So it was on the slide, but I didn't mention it. Sorry.
Thank you.
Sorry, Zane, please.
Hi, so thanks for the talk. I had a question. So regarding the successful common envelope ejections that should be detectable with LISA, do you have any estimates of, say, per year, how many such events you should be able to detect once LISA is operational?
Not yet. I mean, and honestly, none of the simulations that we have tested are detectable. So with this, we couldn't make an estimate. But yeah, we're still working on more of a conclusion part of this.
I think Barry's talk would actually address, kind of be complementary, in some sense of what Javier presented, in some kind of a different regime a bit. And I think you'll be able to discuss that a bit. Sagiv, please.
Hi, thank you for a very interesting talk. So for the failed common envelope evolution, what drives the two white dwarfs to merge?
So in a real failed common envelope, you would have all the drag forces that makes the companion in spiral into the core. In our case, we are just basically artificially bringing them close together until we have mass transfer. And at that point, we leave the simulation evolve on its own, so that it happens on a dynamical timescale at that point. But we just artificially bring them close enough so that there's mass transfer, that it's dynamically unstable, and that's why they merge.
Thank you.
By the way, did you try looking at more massive mergers, more massive compact object, or more massive star?
So the thing for this, we have basically reused all existing simulations that we had. So I don't think we have more than 0.8 in case of white dwarfs or something like that. But it would be really interesting. Like I would be eager to make more simulations of this.
Fabian?
Yeah, maybe just to answer directly to your question. I mean, I think the dynamics of all these phases, this is pretty much captured by the simulations. And of course, if you, for example, want to scale it up or down, you know that the strain signal that you get from the gravitational waves is going to be proportional to the chirp mass. It's not directly the chirp mass, but there's some exponent, but sort of that just gives you an idea of sort of how much you can sort of pump up the signal or boost it and put it up and down. And well, you would have to go probably really, really massive, at least for the main sequence mergers, to make anything working out.
That's certainly true. I think in our analytic model that Barry will present, we discussed this, and the mass ratio is actually also quite important in that sense. Okay, thank you very much. Any other final questions? Okay, let's see. I don't see anyone else. Okay, so let's see what our time. Okay, so actually I think we have a good timing. So what I suggest is we have now the 10 minutes break, and because the next talks are also actually related. So we have 10 minutes break, and after all we have the discussion to. So we're coming back to the second part of the last session for this day. We're talking about the black hole neutron stars, gravitational wave sources, and their relation to common envelope. And we started with a talk about the accretion neutron star and the effects, followed by the talk about the gravitational wave sources or gravitational wave emission during common envelope. And the next talk, Barry will continue on this topic, kind of complementary in some sense, I think, to the work done in the previous talk. So Barry, please upload your presentation, and I'll give you a 2 minutes warning.
Okay, thank you. Can you hear me well and see my slides?
Okay, good. Yeah, you can.
Okay. So thanks very much for the opportunity to talk at this conference. I'm going to tell you about pretty much similar topic to the last talk, which is gravitational waves from common envelope binary in spirals. This is based on a paper that I wrote in collaboration with Hila Glantz, who is also here, Chagai Peretz, Evgeny Grishin, and Vincent Tejac. And right, so let me start. Okay, so the question we wanted to explore is that could one actually see the inside of a star? So we know that it can't be done with visible light. And then the question was whether it could be done with gravitational waves. And what we wanted to do is to derive a simple model that will be able to answer this question, whether gravitational wave emission from common envelope evolution can be observed by gravitational wave detectors such as LISA. Now, people have already discussed gravitational waves from Thorne-Jitkov objects, which are formed when a neutron star enters some giant and goes into its core, and then these gravitational waves and also the gravitational waves emitted by common envelope evolution, they don't arise from perturbations to orbits because of that are caused by the gravitational wave emission itself, but rather they arise completely from the environment. So they depend on, crucially, on how the star's envelope affects the orbit of the companion and the core inside it. And for different density profile, one would expect a different gravitational wave signal. So again, we wanted to create a very simple model. So there will be quite a few approximations here in the next couple of slides. But this model, we believe, can answer at least the qualitative question of detectability and give an estimate of signal to noise ratio. So as you all recall, the gravitational wave strain is proportional to 1 over distance. It's also proportional to the derivative, the second derivative of the quadrupole moment. So here you have the quadrupole moment approximately, and here you have a time derivative squared, right? So indeed, we want as large a chirp mass as possible, but we also want a high frequency. And this is only achievable if the companion is small, so that it penetrates quite deep into the giant before the collision. Right. So so the model we wrote down, it's valid mainly when the companion's mass is much smaller than the giant's mass. And in this limit, we can make the approximation that there is no back reaction, so that the envelope is roughly constant. I will refine this approximation a bit towards the later stages of this talk, but for now, we have a fixed envelope that is fixed to the core of the giant, so they move together, and the companion orbits inside it. So here I wrote down the equations of motion, and the drag force is assumed to be approximated by gas dynamical friction, and we use the model of Oestreicher from 1999. This model is strictly valid for an infinite homogeneous medium, but in a certain because we start the companion already at the edge of the giant's envelope, we believe that this model is appropriate if one defines the Coulomb logarithm correctly. Okay, so this is the differential equation that we want to solve. R is the distance between the core and the companion. And so this is an ordinary differential equation, which is much simpler than the partial differential equations one usually has to solve in common envelope evolution. So here's an example of what one gets. You have a 0.6 solar mass point mass companion. So think about a white dwarf, and 8 solar mass giant. And the motion is described by this plot. So you see it starts orbiting, then it plummets inside, and then it does a few oscillations close to the core until the collision. Here on the right, you can see the gravitational wave signal. So I shifted the two polarizations so that you can see them both. And we stopped the simulation at the moment of collision. Okay. Now, to relax a bit the assumption of no back reaction on the envelope, we run the same simulations, but we take the density profile of the envelope to be linearly stretched by some constant factor, which we choose to be 10 based on other data. So you have to remember that the most of the gravitational wave signal comes from the very end of the simulation. So the initial evolution is not very, very important, as was also mentioned in the last talk. Of course, it's important to set the initial conditions for the end of the simulation, but other than that, one can sort of forget about it. And so this is the linear dilation that we did. And then we ran the same ODE solver with the updated density profile. Okay, and now let me show you some signal to noise ratios. Oh, sorry. So here you have a companion mass of 1.4 solar mass, so a neutron star, and the different colors correspond to different masses of the giant. So in blue, you have a 5 solar mass giant. Sorry, in green, you have 5 solar mass giant. In blue, you have an 8 solar mass giant, and in red, you have a 15 solar mass giant. All of these are calculated at 10 kiloparsec away, and I plotted the sensitivity curve of LISA and also BBO and Decigo. So you can see that sometimes there's enough signal to noise and sometimes there isn't. On the right, you can see the same thing, but with a linear dilation factor of 10. You see that this increases the signal to noise ratios somewhat. Okay. And of course, if I lower this mass, the peak frequency would go to the left, and the amplitude would also go down. So this is a trade-off, really. Now, of course, in the end, you want to know if this approximation is correct. So we compared with hydrodynamical simulations. The code is the same code that Hila described in her talk on Tuesday, and spared me the need to explain it again. So we took a hydrodynamical simulation, and the density profile dilated by a factor lambda. The initial density profile dilated by a factor lambda, and started both simulations in the same initial condition. And then we ran them, and you can see that the distance between the core and the companion as a function of time in both cases. You can see that they are roughly in qualitative agreement. At least the time scales are correct, and also the decay is approximately okay. And also the signal to noise ratios for both agree, at least until the resolution that the SPH simulation can have. And it's a problem to sample the simulation at a frequency of a few millihertz for such a long time. So we just sampled it at a lower frequency, and that's why the blue line is cut, right? But the main take-home message from this plot is that the simplified model, the semi-analytic model, is good enough to give you an estimate for the signal-to-noise ratios and the possibility of detection, but of course not good enough to give you an exact gravitational wave template for which you would need for LISA. Here's a summary of
2 minutes.
Okay, thank you. Here's a summary of the signal-to-noise ratios for all the cases we considered. I highlighted the cases where there's enough signal-to-noise, possibly enough signal-to-noise to be detected in LISA. 11 is a bit marginal. Actually, 20 and 21, if we have good templates, then that's fine. But if not, that would also be a problem. So you see that there's a possibility of detection if this merger happens in our galaxy. Right. And of course, let me mention that because the companion is very compact, I'll mention it here. The companion is very compact, and the giant has a much larger mass. Then we expect that such common envelope mergers will always be failed mergers, so that the envelope is not ejected and there's a merger at the end. And this is, of course, something that has to happen in our semi-analytic model, but also happens in the numericals, in the hydrodynamical simulation for such extreme mass ratios. Okay, so to summarize, we saw that gravitational waves are indeed emitted by common envelope evolution. Most of the power is at the end. The frequencies are compatible with LISA, but the amplitudes are a bit low for galactic events, and for extragalactic events, there's no chance currently. But future gravitational wave detectors that improve upon LISA's sensitivity might be able to observe them. And the simplified semi-analytic model can indeed give good predictions for the characteristic gravitational wave strain. If you have any question that you won't have time to ask me right now, you can ask me on Slack or send me an email, or you can look at our paper. Thank you very much.
Thank you very much, Barry. Please feel free to ask any questions you have. Yes, Fritz.
Yes, Barry, thank you very much for this nice talk. I have A question about your hydro simulation. So how do you know actually that in this case you get a failed common envelope and a merger in the end? Because I mean, in the end, you don't spiral in that deeply, and the simulation looked very similar to what Javier has shown before, right? So if you go back to the slide where you show the orbital evolution of the semi-analytic model or the analytic model and the here.
Oh, sorry, this one?
No, the one where you show the orbital evolution.
Oh yeah, this one.
Here. Yes, exactly. Yes. The right-hand side plot.
So in this specific simulation, we carried it out all the way to the end, and indeed the particles did collide. I mean, the core and the companion did actually merge. So that's why I know in this simulation. The reason I said I would expect a merger of the companion and the core and not a complete ejection of the envelope is that the companion has a relatively low mass. So it is more probable that it would sink in before ejecting all of the envelope. But of course, this might not be correct if you have other data that say otherwise. Our approximation, let me say that it always gives you a merger because it cannot do any, because there's no back reaction.
Yeah,
there's no possibility.
In the analytic model, yes, but in the SPH model, that may be different, right?
Yes, in the SPH model, of course, that may be different. In this particular simulation, there was a merger at the end, yes.
Can I add to this? So we just define a merger when we get to the smoothing length. As you can see here, it's just the purple line. And we chose it such that it will be small enough. So we can actually say that a merger should happen. We did not simulate the merger itself. We just got to this point. And actually it happens a little bit after, I think, this, like in the continuing of this graph. Yeah, I think that's more or less what I wanted to say.
Yeah.
And another thing is about the ejection. And of course, we did not successfully eject the envelope in this case with any of the prescriptions for the mass loss.
Yeah. Well, I mean, from our simulations, what we see here is that also the in-spiral usually stops. And that is unrelated to whether or not we eject the envelope successfully in the end. Of course, on the long-term time scales, you may still then merge, but not in the initial plunge in. So the depth of the initial plunge in is more or less independent of whether the envelope ejection is successful or not. And then whether or not you have a merger, I mean, that, of course, to know that, I think what's necessary then is to actually sort of vary the smoothing lengths and see whether you actually end up at the same distance or whether you really always spiral into this smoothing lengths, right?
Mm-hmm. Yeah, so we actually did this. We had a few simulations for the same case, and they all ended with a merger, like what we defined a merger.
Thank you.
Yeah. So just to say, so for this particular simulation with these particular initial conditions, indeed it came out as a merger, but of course other initial data and other masses might give different results. Yeah, that would be the full answer to your question. But of course, I think because the gravitational waves are mostly emitted at the very end, if there's no merger and if the distance between the core and the companion doesn't end up being quite small, then at least as far as gravitational waves are concerned, there's not going to be much of a signal if there's no merger.
Yes, I agree. Yeah.
Thanks for the question.
Agai, you're muted.
Sorry for that. So thank you very much both for Barry and for the questions and this short discussion. Of course, we have some time more discussion later on. Mohammed, please upload your presentation. Okay, excellent. So,
hi everyone. Can you see me, hear me?
Yes, excellent. So I'll give you a 2 minutes warning. So please begin.
Hi everyone. My name is Muhammad. This work was done by me and Noam. Actually, I'm talking about the triple stellar system that we have simulated using flash code. Our initial conditions were just the results of the MESA code, density, pressure, temperature profiles.
Muhammad, did you move with the slide? We still see your first slide.
Yeah. Not yet.
Okay.
I'm just telling a short story. Okay, then I start. So again, I'm simulating a triple stellar system. I'm talking about two neutron stars that will swallow to a red supergiant star. Then we investigate the energy released from the merger of the two neutron stars with the inner envelope of the red supergiant star. So here I start to the second slide. So our evolutionary route is as the following. We have two neutron stars. Each one is 1.4 solar mass with a main sequence star. And then we define a first phase, which is neutron stars enters the red supergiant envelope, and each neutron star launches two jets to the opposite directions that power a bright event and inflate the envelope to largely huge radii. So this takes about the order of months, and the energy of all the jets, we have 4 jets, 2 jets for each neutron star, 10 to the 48 erg to 10 to the 50 erg, and the mass, or the accreted mass that we assumed here, 10 to the -4 to 0.01 solar masses. Then we define the second phase, in which we have the two neutron stars merge together as a result of tidal reaction and interactions and the accretion of mass. Then they merge and they explode in the inner part of the envelope. This takes 1 second, and the energy we expect here 10 to the 50 to 10 to the 51 erg, which is proper for the supernova explosion. And the remnant, or the product of the merger, this merger of the two neutron stars, is just a heavier neutron star or a black hole. Then the third phase that we actually simulated here, this is the only phase that we simulated, sorry. And here we see how this merger explodes the inner part of the envelope. And here we also show the shock wave that comes out from the explosion. This shock wave takes about several weeks to reach to the surface of the red supergiant. Now, we don't simulate the total time, this total time of several weeks. We only simulate for 10 hours, since we see our main results in these 10 hours. Okay, then we have 2 options: that the neutron star black hole merger remnant does not enter the core. The core explodes as a core collapse supernovae, and the remnant will be neutron star black hole or neutron star black hole, a binary, or neutron star black hole merger remnant enters the core, and with the jets it launches, explode the star remnant, and then a black hole. And again, we only simulate this phase inside this red rectangle. Okay, we don't simulate the previous phases. Here I show the density profile. So we have here 2 times. The blue one is at the onset of the common envelope evolution, and the red one is after 3 years of the common envelope evolution with Jet's energy before the merger. Okay, and in our simulations, we simulate after the merger. So we don't talk here about the years or months. We have only hours, okay, the order of time. And also here I show the density and mass profiles only in the inner part of the envelope in which we are interested. Okay, we want to see how this explosion affects or deforms the inner part of the envelope. So I show here at between 0 and 20 solar radii, the mass and the density. The blue one is the density, and the red one is the mass. Just to be accurate, here we have at the 0.64 solar radii, we have a helium core, okay, which we don't simulate. It is a point mass in our code, and we look at the interaction between the energy released from the merger and the gas that above this core. Okay, so in our simulations, first of all, we use Flash, which is a very good code. And the gas here is optically fixed, so no radiative cooling being used. We also have three pressures. We have a radiation pressure, okay, the pressure of the ions and also of the electrons. So we have three pressures. Okay, this is very important, and it took a long time to learn this problem, how it changed with the different pressures. Also, we have a point mass gravity at the stellar center. I assume here 10.1 solar masses as a point mass gravity, and we don't have self-gravity, okay? The simulation that we concentrated here is, I call it S2, so the inert core in the code is only 2 solar radii. Okay, and the location of the merger site is at 50 solar radii, and the energy that I assume is 10 to the 51 ergs. Okay, so I start here to show results. I start from density maps. So here in the T0, the initial conditions of the code, here we have the center of the red supergiant, and here in the yellow circle, we have neutron star merger site where we set the explosion, okay? So we don't see yet the explosion, but we start to see it here, okay? So as I said before, we run it for 10 hours. Here we see also the shock waves. For example, at t equal 3 hours, we start to see that the shock wave closes on itself at about 30 solar radii from the center. I also plotted here 3 density contours at the values of 10 to the -7, -5, and -4, okay, to see how it evolves with time. So notice that in the final times, t equal 4, 6, and 10, that the envelope is highly deformed, and the inner part returned to a more or less spherical structure here in the last one, which is very good. Also, I show here the velocity maps. So even here we see the shock waves much more nice than before. Okay, for example, here is the shock wave at t equal 1 hour. And please note the different color scale in the panels above. I mean, the color bar above each panel is different between the different panels. Okay, and more results with the temperature here. Again, we see the shock waves. Also, the shock waves here closes on itself at t equal 3 hours. Okay, and our main result is we actually try to calculate the bound mass in the inner part of the envelope. Okay, so how did we do that? We thought about the mass that stays bound within the inner 20 solar radii and 40 solar radii. And we calculate this with time. So at any time t, we have the total mass that stays bound within 20 and 40 solar radii. For example, here for the upper group of these lines, we have the envelope mass inner to 40 solar radii in the different cases that we have simulated. And in the lower group, we have the same mass, but I mean the bound mass within 20 solar radii. the envelope mass is the mass above R equal 0.64 solar radii, which is the radius of the core. Okay, this is very important. And the two lines for each simulation have the same color. Notice here, for example, this cyan line, cyan is a nice blue, yeah, for the 40 solar radii, and here the same parameters, but at 20 solar radii. For example, I would like to compare between
2 minutes. Okay.
Okay. I don't need more than that. Very nice. Actually, I want to compare between two cases. The first case is to look at a merger that occurred at a distance of 25 solar radii, but the energy is 3 × 10⁵ erg. So it's according to our results or our parameter, this is a low energy. Okay, so I compare this with a farther. I mean, more the distance of the other explosion is more far and more energy. So more far, more energy, I compare it to the closer one with lower energy, and I get at the end of the simulation about the same mass. I mean here the dashed cyan line with this black one, okay? And here I actually leave you to read my conclusions. Thank you.
Thank you very much, Mohammed.
Thank you.
Any questions, please? Yes, Enrique.
Hi, I just wanted to know what's the orbital separation between the two neutron stars as you enter the common envelope?
Okay, so here in our simulations, we don't have this, so this is not important. We only assume that they are merged, but in general, the distance between them is very small, or maybe tens of kilometers, or maybe Hagai or Noam know about this more. But here, in my simulations, I did not assume anything about that. I only assumed that they merge.
Okay, thanks.
Other questions? So Mohammed, the jet penetrates all the way out?
Yeah.
So how would it look like, do you think? Would it be a long GRB? What would it look like?
Well, we can compare it to supernovae, but I'm not sure that it's like the GRB.
Paul?
Yeah, interesting talk. So the the neutron star merger occurs because of gravitational radiation, right? So if it's just, and the time scale for that, is long until the last minute, and so you've assumed that it's just about to do that when it enters the common envelope. Common envelope itself is also a pretty short interval of time. So I'm wondering, how common would these events be?
Okay.
It's to require a coincidence of these two very short-lived events.
So I may back to this evolutionary route. So here, as you can see, for example, the merger, took here the jets that were launched from the neutron stars, they took months. I agree with you about the time scales, but I need to think about that.
I can answer this because it was not part of this project. It's a different issue. The issue is that the two neutron stars are close enough. They might have merged in a long time, but when they enter the common envelope, they suffer a gravitational drag, and also they can accrete a little bit mass, and this causes them to come closer and eventually merge and releases energy. The amount of energy we took here is the amount of energy that people estimated from the kilonova. And we substitute it in the envelope and deposit it in the envelope spherically, because kilonova, according to models, eject both equatorial and polar outflow. So we assume spherical explosion, but it is the envelope, the red supergiant envelope, that forces the two neutron stars to merge in several months. This is a point. It has other implications beside this event, which would be very energetic because of the jets that they launch. It will be like a supernova, but last for months and maybe years. Another outcome might be that if these jets, if the merger did take place, it will shorten the time scale at the early universe, at the early galaxy evolution of merger of two neutron stars to form our process at early times that observations require. Isolated double neutron stars seems not to give this short time. So that to answer the question, the red supergiant by dynamical friction forces a neutron star to merge in few months, several months, maybe a year.
Well, we studied this, right? Hila studied this with typical common envelope pollution, and even simulated it not for these masses, but one still needs to be careful because you want to merge the neutron star. You need to be very, very close where the gravitational energy is huge. So the amount of mass you need in order for the dynamical friction to do that, is quite considerable for such a short period. So that's one does need to be careful about these issues. And study this in more detail, of course, later on.
Yes, the general picture includes merger only close to the core, like 50 and 25 solar radius, and sometimes not. So both of them might get to the core or not merge. Yes, so I agree.
Okay, thanks.
Any more questions? Actually, I think we can now continue to the general discussion. So feel free to ask questions of any of the speakers, and of course, raise other questions related to aspects of common envelope and gravitational wave sources and compact objects, and what we can learn from them. I think it's actually also related to some of the previous talks even before this session. So I want to actually maybe follow up on the early discussion. What do you actually need in order to really study the accretion onto compact objects during the common envelope evolution, and how this affect the spin and the alignment of all of these? So I think they mentioned some methods, both analytic and numerical. But what would be the next step, do you think? Yeah, Paul.
Yeah, I think the kind of simulations that Miguel Delgado talked about, GRMHD simulations of the vicinity, the accretion disk itself and the vicinity of it interacting with a wind tunnel type of boundary. And the question there is how best to connect that to the resolvable scales in a global simulation, in order to construct an experiment that's plausible. But I think getting those length scales in a global simulation, I don't think that's really feasible.
I completely agree. The question is, are we as a community going into zoom in simulations like they do in cosmology? Because I don't think I know of many such really zoom in. But in some sense, I think it is time to go to this next step of doing a global simulation and do a zoom in on the particles with this boundary conditions you just mentioned. Does anyone in the audience work on this kind of zoom simulation at this point?
I don't know of anybody, but we are certainly thinking about and starting to perform some simulations like this, where we're just trying to get insight into the appropriate subgrid model to put into global simulations.
Okay, I think we might actually, maybe we should actually contact people from the, in a sense, other communities working on accretion on compact objects, and really give them our boundary conditions for them to use. I think that might be interesting collaboration, and that I think we should actually start these days. A different question, how about alignment? When you start with a rotating star, right, or even slow rotating, and you start the companion in some misaligned stage, how much would it align, or how fast would it align? So in the end, we should expect maybe a spin orbit, colline spin orbit. Okay, I guess no one is working on these issues these days. Going to a different maybe direction. So what can we actually learn from observation of gravitational waves sources right now? So I think people mentioned some kind of constraints on alpha in some sense. Can we do more than that? What are the ideas out there?
Can you repeat the question, Hagai? My internet broke when you were just saying it.
Yeah, sorry. I was asking about what can we actually learn for common envelope evolution from gravitational wave sources. So people already mentioned some constraints, potential constraints on alpha formalism. Can we do more? Can we do other things? What can we actually learn from these, and how can we interact with these new observations?
Well, provided that you actually see something in a gravitational wave detector, you might use this data. You might combine this data with an electromagnetic counterpart, and that will actually tell you about how to calibrate the gravitational wave signal with the density profile of the envelope at or the remainder of the envelope at the end of the gravitational wave of the merger and or of the common envelope evolution stage, and then further compare this with numerical simulations. You might be able to know something about the original density profile and the initial conditions, but that's maybe a bit far-fetched.
Yeah, no, I agree with you. I think if we could potentially hypothetically detect a full signal, we could see how quickly the frequency changes and kind of model the drag forces and the density profile at the latest stages of the common envelope, and that could help modeling these things even better, I guess.
Alejandro?
So there's a couple of things that I think could be good, and there's probably more. But the first one is Mathieu Renzo at Flatiron recently suggested that maybe you can see with Lisa if the common envelope doesn't lead to a merger, that you can actually have a common envelope and then have the inner binary that you might not observe, like you might not resolve optically because of what we already discussed yesterday about luminous red novae and the obscuration, but that maybe you can use Lisa for that. So I haven't thought a lot about that, but there's a paper, I'll post it in archive if people want to see that. And the other thing that maybe is not that direct, but I've been thinking about using LIGO sources, particularly their masses, to see if you can distinguish between how the remnant mass can correlate to avoiding or not a second common envelope phase. So I think maybe sometimes with LIGO sources, it's difficult to go back all over to the first common envelope because there's a few things going on after it. But if there's a final mass transfer episode just before the common envelope, sorry, just before the gravitational double compact object formation, then maybe you can say something about that final mass transfer episode. And that sort of mass transfer episode is expected for double neutron stars and neutron stars and black holes. So I am thinking that the measurements of mass could lead to, like, avoiding this final mass transfer episode could lead to more massive systems, and these more massive systems therefore would lead to more massive neutron stars or black holes. I will just post now a paper where I talk about this, that it was recently out, and I'm trying to address the referee report.
Miguel?
Oh yeah, yes. I'm also a fan of the possibility of peering into stellar interiors as a way to constrain common envelope evolution, given that it seems hard to constrain alpha just with the population studies. And of course, I would imagine that each particular system might have its own alpha depending on what the detailed physics is. One other possible, I guess, gravitational wave source, I think, that I had worked on a while back was if you have, you can have gravitational wave emission from neutron star rotation if there's any asymmetry on the crust, and that could, that's certainly one of the sources that LIGO is looking for in terms of galactic pulsars and whatnot. But of course, an uncertainty is the crust physics that might allow for that, and then also what rates we might expect for common envelope in the galaxy. So I guess for the binary pop synth folks, have there been any recent updates to how often we expect compact object common envelope evolution in the galaxy?
I don't know if Sylvia or Sylvia here. I don't know if the BPS people are around.
I think for heavier double compact objects, or things that will become double compact objects, it's not very promising just because of the rates, but I don't know about with white dwarfs.
What about electromagnetic counterparts? Do we actually expect somehow to have remnant gas around when the compact objects merge, especially if you have a neutron star involved and you have some kind of electromagnetic counterpart and that could interact with this remnant gas? So I think people do see in observation, right? And please correct me. We see this circumbinary disk, for example, in some cases, not necessarily for massive objects, but at least for low mass objects. So if those exist also about massive stars, then we might expect in short GRBs, for example, to might interact with some remnant gas around. That should potentially be observable if such an interaction exists. Alejandro. Sorry, I don't know if you're
Yeah, so thank you. This is, I think this is a very important question, and what I would like to know, maybe if someone can comment more, maybe you or but particular observers, what do we need? Like, what sort of conditions do we need to have a possible electromagnetic counterpart from this previous common envelope ejection, or what conditions will not give us this electromagnetic counterpart? Because I don't know much about this, but I've heard that with supernova, sometimes you need that the CSM need to be at a certain separation and with certain density, and therefore the velocity needs to be, like, there are some constraints, like you're not as free as I theoretically thought. So I don't know if anyone has maybe a few sentences of description of what would make a system ideal to be observed in such a scenario where there was a previous common envelope, and then now you have maybe, let's say, a binary neutron star merger or a black hole neutron star merger where you expect some ejecta, or whatever electromagnetic thing that we could pin down and understand better.
Yeah, Dana, please.
Yeah, so I'm not sure about what I'm going to say, but maybe in the theme of peculiar supernovae, like supernovae that have more peaks on the light curve that we discover now and then, if we can find like an electromagnetic like the counterpart of the gravitational wave emitter, we can understand something about the origin of the supernovae. Yeah, but I'm not sure if that's possible.
Yeah, well, hopefully we will have at some point such electromagnetic counterpart. I guess we don't have it yet, but I guess with more and more gravitational wave sources, we might have a better chance of observing these.
Because the problem in all systems of common envelope, they're very opaque. We cannot see what happens inside. So there are many things we don't know about the origin of such systems. So maybe gravitational waves or other outcomes can help in this respect.
Yeah, the point Eldana made is that if you have a peculiar supernova, really peculiar, long-lasting light curve, very energetic peaks that might be, we think, powered by merger inside and jets and so on. And if it's a merger with neutron star with a core, or neutron star with neutron star, as Muhammad showed in his talk, then we will see a supernova coming with a gravitational wave. So maybe instead of asking what electromagnetic counterpart we have to gravitational wave, we should look into peculiar supernovae and see if in one of them, they're supposed to detect now 10 to the 4 per year. Maybe in one of them, we also will detect gravitational wave. This is a point, yes?
Yeah, I think, of course, this is much more likely in the era of LISA, I think, when we have white dwarf mergers, which might be much more frequent, and that would be, of course, one case, one very interesting case, I think. Okay, any other suggestions?
Yeah, Hagai, I will answer your question before. It's a good question. I thought about it a lot, about misalignment. And let me share something if I find it. I don't know if I find it. I'm supposed to have it here. Just a minute. Need to share a screen, but I don't see it. Okay, now I see it. Can you see my screen?
Yes.
This is from a paper that just was accepted for publication in Astro PH. So I try to come here with misalignment of orbital of 2 stars, the orbit of 2 stars and their spin. I did it with 3 stars, excuse me. So for example, if you have binary neutron star or black hole or even main sequence that enter the common envelope, but the orbital plane of the tight binary system, the inner binary system, is inclined to the triple star orbit, then the jets will be inclined as well, and the merger will be inclined. And I suggested that what we have here is that the jet actually deposit angular momentum to the envelope, in the sense that if the jet, for example, here collide with the envelope, it gives it spin in that direction. The other one escape out. So I don't want to get all details, but from triple star evolution, eventually you can end up with misaligned binary. It can be this binary by some interaction, and I showed it here. I don't want to get to the all details, but in some triple star evolution, we might get misalignment in different direction. Another effect is in binary. If at the end of the evolution, you look at my drawing, we have 2 stars that end the common envelope evolution. This is a core that will, after explosion, become a neutron star or black hole, and this is a neutron star companion. But now you have a circumbinary disk. So this is rotating with the Keplerian velocity, and this is rotating with the Keplerian velocity. But if you look from the point of view of the neutron star here, it sees this velocity actually in the other direction because it rotates faster. So it sees this velocity going in the other direction. The question, I don't know, maybe somebody can tell me if the accretion into this point mass will be from that direction, that it can actually flip its spin relative to the orbital motion. These are my points.
So actually, that's no. These circumbinary binaries are quite difficult to model. Many people actually work on them both at very different scales, both for massive black hole binaries in a disk, but also for planets and also for compact objects. It's still, I think, quite debated what happens actually in that sense. So where do the torque goes? Not even going into the actual accretion on every single one of the object, but even what happens to the binary because of different torques. But hopefully this would actually be answered in the coming few years. I think more and more models are coming up, and I think they would at some point converge to understanding of this aspect. I do hope.
So you think an interaction with circumbinary actually can flip? It cannot tilt it. It's either give it enough angular momentum to flip it or not. But can it flip it? I don't know.
Yeah, I don't think
by accretion. Because if I look at the neutron star, it's rotate faster than this material. So if it accretes, it will have some angular, but I'm not sure because it has more angular momentum relative to the center of mass. So it's a complicated problem. So I mentioned it as one possibility, not in this paper, in another, but I'm not sure it will work. I don't know. This in triple, you can get different things, but they are, not so common. But still, we can explain some misalignment with triple star evolution. So this is my point, answering your misalignment and so on.
Okay, thanks, Noam. Enrique, please.
Yes, to address Noam's question here. So I would guess it would depend a lot on how you want to accrete. If you are accreting through the magnetic field of the neutron star, then you will have a very different lever arm as if you're accreting to something closer to the marginally stable. Well, it's a neutron star, so probably you are outside of that. But if you're accreting close to the surface, it would be probably very different result. And also it would depend on how much mass transfer you can put in it. If you really want to affect the spin, for example, of a black hole, you need to accrete a substantial portion of the black hole, since you're doing it with a short lever arm. In the case of a neutron star, magnetic field could probably help you transfer more efficiently angular momentum, but I guess you still need a lot of mass to alter significantly the spin. That's my guess, but I have not done the calculations. I'm just extrapolating from what I've seen with black holes.
Enrique, the magnetic field is a very good idea. I didn't think about it. It gives you a large lever arm. Well, very good. I think about it. Thank you.
Right. Welcome.
Thanks, Enrique. Okay, I think the hour is already late. We're actually close to the closing time anyway. So if there aren't any last questions or comments that people want to raise,
maybe comments by a young person, somebody who would like to share, because we are old people, we talk all the time.
Oh, no, you just got older today, but other people are still young. Okay, so let us meet tomorrow in the regular time, 1 GMT, and we'll talk. I think the next session is about accretion and jets, if I remember correctly. So see you tomorrow, and feel free, of course, to continue the discussions over Slack, and of course that will be can be seen by everyone all the time. Thank you, everyone. Good night, good morning, good afternoon.